Come back again. So we are looking at regressions algorithms under supervised learning, and last time we looked at simple linear regression and multiple linear regression, and we want to continue from there, and they want to see how we can enhance our multiple regression now, the model we had last time, by incorporating polynomial features to capture potential nonlinear relationships between advertising budget and sales. This approach can reveal diminishing returns or accelerated effects that simple linear terms might miss. And don't forget, our last data set we used was based on social advertising, and we tried to look at various budget advertisement measure on sales, Facebook, YouTube, and newspaper. And when you talk about polynomial regression, it's basically a relationship between the independent variable and random variable when it is modeled as an nth degree polynomial function, which means the n is no more linear n, is now power n with index. What it means, in algebra, we have a linear equation, we have a quadratic equation, we have polynomial equation. Linear equation simply means that there's a linear relationships, which means 2s plus s, just one power of s is 1. Then quadratic equation means you have 2 power of s, which means 2s squared, and so on. Then for polynomial, you have a higher power of s. Higher power of s, poly means many. So polynomial means many power or many index. So in this form, we have many power of s. So we can why polynomial feature is used, because most times in real world relationships, often the real world relationship often aren't perfectly linear. Sometimes they can be exponential, they can be polynomial, so they are not always linear. So our data settings may possibly have diminishing return, or at least each additional dollar has a less impact. It could also accelerate effect. Have accelerated effects or accelerating effects, which means after threshold, the impact increase faster. Or it could have polynomial terms, e.g. Facebook square, let the model capture these curves. So when you have Facebook square, it should be curve-based plots at the end of the day, because that cannot be captured by a linear model. All right. So we want to see how, if possible, we can find any linear effects. Any nonlinear effect in this particular data set using polynomial features. So we are going to just apply our data set we have used before. But before that, if you look at this simple chart here, we have simple linear applied to a data which is not linear. As the data is not linear at all, you can see it's curve. So this particular data set requires a polynomial feature or function to capture it. Can you see? So this is a polynomial function to capture a non-linear data set. So that is exactly what we are talking about. So now let's introduce our data set as usual, the one we have used before. We have loaded it. So we have used this one before, just load it again. If you remember that we have run this particular line of code last time, we only introduce a new function here, new libraries, polynomial features, possibly make pipeline. So other ones has been used so far. So this is our data set called social marketing, and we are looking at 3 columns here, which are features, YouTube, Facebook, and newspaper. And our sales, who happen to be our target variables, is being applied. So we are now splitting our data into 80 by 20 percent, which means 80% training, 20% testing. You can change that as case may be. So which is indicated in this particular test size here, which means 0.2 means 20. All right. So now we can implement our polynomial regression here by creating a polynomial feature, and we just call the function here, polynomial feature here, which is degree 2, which is power 2 power. So you can do 3 power as well. So, but to see the better effects, but let's just do a sample here. If we run this one, we run this. Now what we have here is we have the generator give us the computer the features. So feature means we have YouTube square, we have a Facebook square, newspaper square. So in the feature that generated, all right. So we are trying to generate a 2 power now, okay, so that you can see effect on the polynomial function. right? Because our data is not actually yielding to that, but we want to see if you can at least find something close to that. So let's fit the enhanced model now. So we are creating the model now by applying the make pipeline, standardizing the data set by using standard scalar. So we get our coefficient by printing out this. We run this. We print out the coefficient for Facebook. We have 5. We have this. This is a parallel linear YouTube now without anything yet. So and Facebook and the newspaper. So when we power the Facebook, we have Facebook square. We have a YouTube square. We have newspaper square. So these are what we have currently. So let us evaluate the model now. I mean, just not the model only now, evaluating model improvement now, because we want to bring in the linear to compare with the polynomial. The linear I'm talking about now is not just linear now, it's now multiple linear. Don't forget, it's multiple linear. So we have linear model here. We have we call it function here. We run this. If we run this line of code now, we have our this. So we have polynomial regression here. So our this is our linear. So we want to fit in now, predict it here. So we want to compare by the R square between two of them. All right. So we do the comparison here. You can see the result here. All right. So when we print out the result, we have a linear model which is 0.89 and the polynomial 0.98. You can see the difference is very high. So this one gives 89%, 98% approximately. Don't forget, this is a multiple linear model. Don't forget, because we are using more than one feature. Don't forget that we are using the 3 features in our data set. Because if in the simple linear effect we got 0.6767, I remember 6767. That is what we got in the simple linear effect. But in the multiple linear effect, last time we got 89.72. So, and in the polynomial effect now we are having 98.65, which is higher. So the polynomial effect practically untypically shows a 0.09 approximately improvement over the linear fashion, over the multiple linear fashion, so to say. So let's see if we can get a feature nonlinear effect also in this case. So we are going to run we're going to call our Matplotlib library and run the features here. Go to the code this particular one again. Okay, so just to make the code it will be one page. So we run the model again and see if we can get a visualization. So if you run this line of code now, you can see we are trying to make our YouTube and newspaper constant while we use Facebook and sales together. Okay, so that is what we are trying to do here. So now we can run here. You can see this result here. Our title head here. So you can see here. So it gives us the nonlinear effect of Facebook advertising on sales. Give us a linear shape, and there's a reason for this actually. Because when we run this line of code, we have a coefficient for Facebook square is equal to 0.0009, and if a coefficient for Facebook square is too small, that is 2 to 0, it means that there is no linear effect. There's a no non-linear effect. That's what it means. So our model coefficient is this, which is we have got here. Since this value is near 0, the terms has no particle effect. Okay, that's why it is linear. It is a straight line. All right. So if the curve flattens, diminishing returns occurs. If it steepens, accelerating effect occurs. But if it is U-shaped, optimal spending range exists. So our YouTube scale and Facebook square tabs often show diminishing return, negative coefficients. Okay. So what we have done so far, actually, we first transformed our features to polynomial space. The model is trained on these polynomial features. We visualize using the same transform space, and we hold YouTube and newspaper at their mean values, while we now look at we vary only Facebook budget with sales, and we show the prediction change non-linearly. So alternatively, we can also use another method by using 3D to visualize our YouTube and Facebook combined together in one chart now. So while we make the newspaper at a mean value, can you see now at mean? So we are going to combine YouTube together with Facebook on a particular chart using 3D, then together with sales. So if you run this line of code now, you see that we have our don't mind the warning. We have our YouTube and Facebook together now. So this one is a curve. Can you see it's curved a little bit now? Yes, it's curved. So we have our sales here, predicted here, Facebook budget, YouTube budget here. You can see here. So the 3D surface shows how the interaction between two ad channels affects sales. So they affect the sales. Okay. But polynomially, you can see two of them are polynomials, a little bit curve. So, but that curve could not be seen in one line of the one we did before, that which was linear. So we can also do a forceful effect by forcing a feasible curve. This is not actually based on our data, but we are using this to demonstrate what we have learned on polynomial, because our data does not conform to polynomial effect actually. So we are going to create artificial quadratic relationships between these parameters, and we are going to see how we can generate a curve that we are talking about in polynomial if the data permits it. But in this case, our data does not give room for that, so we are going to create artificial one. So this is a quadratic equations relationship now. So we pass our Facebook square now. So we're trying to see how we can square it. Then here we now create our plot here. So if you run this line of code now, you see your plot here. So this plot is giving us this artificial, just to prove the concept we are talking about. These are data, these are quadratic lines, you can see here. So this curve shows that this Facebook budget and sales, which we are looking at before, which now is this Facebook square now. So it's giving us a curve shape. But this curve shape, like I said before, is not based on directly on our data, is artificially coded. So since even forced quadratic fitting shows a line, Facebook had to have a purely linear relationship which with sales in our data set. That's what we had originally. So no evidence of diminishing or accelerating returns in this spending range. So the indication is that each dollar spent has consistent impact, no optimal spending threshold. So for analysis, we could actually report the linear relationship directly, so that which is the best thing to do. So note also that no diminishing returns were detected in our data, and I will suggest also that we can test with higher budget ranges, so that we can see the effect if possible. All right, I think that is that we have today on the polynomials. We will see more of that as we continue. Don't forget, we didn't do much. We didn't run our performance as usual, because today it's not necessary. You can do that. You can just introduce that yourself. We have already seen our performance here, so you don't need to do much. So on that. So thank you so much for listening. I will see you in the next class as we continue on that. It is machine learning training, and if you like, you can comment, you can share, you can also like. We'll see us in the next class. Thank you. If you have not yet subscribed, I will plead with you, please go ahead and do so that you can enjoy more of this particular class.